we're drawing free body diagrams, we are drawing the forces acting on an object. We're representing those forces with arrows. The length of those arrows matters. Because we're representing forces with arrows, the length of the arrow tells you how strong the force is. So when you're drawing an arrow, you have to give the arrow a name tag. We talked about that last video. But not only do you have to tell us what type of force it is, you have to pay attention to how long your arrow is to represent the strength of the force. And of course, the direction of the arrow matters because forces have a direction, and we have to show which direction the force is acting. So there's this thing called net force. Net force is the same thing as the total force, meaning if you added up all the forces acting horizontally or all the forces acting vertically, you get the total force in that direction. So if you have a bunch of horizontal forces and you add them up, that would be the total force or the net force in the horizontal direction. I'm not going to get much into this right now, but I'm just going to show this to you. We represent net force or total force with this funky looking thing, which is the Greek letter sigma, and this means the sum or add all the. So this means the sum of all the forces or add up all the forces. So the total force, the net force. The reason I told you that is because what you need to know is that if an object is at rest or moving at a constant speed, the net force on the object is 0. What does that mean? Well, if an object is at rest or not moving, or moving at a constant speed, that means its speed isn't changing and the object is not accelerating. So in either of these cases, the object is not accelerating. If the object is not accelerating, that means there's no net force acting on it. There's no total force acting on it. So here's a stack of sticky notes, right? If I push it to the left, it's going to accelerate to the left. So there is a net force to the left, a total force to the left. Now, if I push from the right and I push from the left, the total force or the net force is actually equal to 0 because the force to the right cancels the force to the left. So even though there's two forces, when you add them up, because they're acting in opposite directions, they cancel each other out. And the net force would be equal to 0, which you can tell because the sticky notes are at rest. The same idea would go for something at a constant speed. The net force, the total force, would be 0. That means that all the forces cancel out, so there's 0 acceleration. Hopefully this video hasn't made you cry so far, but I might cry because here's an onion. The next free body diagrams I want you to do are going to be for this onion. So I'm going to throw the onion up in the air. It's going to go up and then come back down. So you're going to draw a free body diagram of the onion. After I let go of it while it's on the way up, when it's at the very, very top, and when it's on the way back down before I catch it. Got my onion. When we're talking about free body diagrams, we're thinking what forces are acting on the object. Our object is the onion. Once I let go of it, what forces are acting on it? Well, the object is in free fall. There's nothing acting on it besides the force of gravity. Remember, we're neglecting air resistance for all of our problems, so the only force acting on it is gravity. So I'm drawing 3 free body diagrams of the onion, one when it's on the way up, one at the very top, and one when it's on the way down. So remember, we said when we're drawing a free body diagram, we draw our objects either as a box or a point. I prefer to draw my objects as boxes. So we're going to have 3 free body diagrams. So I'm going to draw 3 boxes, and that box is the onion. So when the onion is on the way up, what forces are acting on the onion? Well, we already said the only thing acting on the onion is the force of gravity, which points downwards. So our only force is going to be the force of gravity pointed in the downward direction. So we're representing our forces with arrows. The direction of the arrow matters. Because gravity points down, our arrow is going to point downwards. Remember our second rule for free body diagrams, the tail of the arrow has to touch the box. And finally, I have to give this arrow a name tag. I don't know what this is until you tell me what it is. And because this is the force of gravity, I'm going to label it F sub G for force of gravity. Right, F is force, and the G is like a name tag for the force, telling me that it's the force of gravity. So what about when the onion's at the top? The onion is still in free fall, so the only thing acting on it is still the force of gravity. And make sure that this arrow is the same length as this arrow because the force of gravity hasn't changed. The onion has the same mass in both cases, right? So the force of gravity is the same strength, so your arrow should be the same length. And on the way back down, the onion is still in free fall. So the only force acting on it is still the force of gravity. My arrow is the same length and in the same direction because gravity didn't change. All three of these free body diagrams, they're all the same, whether the onion was on the way up at the top or coming back down, because the only force acting on it was gravity because it was in free fall. So a free body diagram doesn't tell you like which direction it's moving, right? The free body diagram just tells you about the forces acting on the object. And so notice that we only have one force on this free body diagram, which means the net force is not equal to 0. There's nothing canceling out the force of gravity. So there is this net force or total force acting on the onion, which is why it accelerates, because there is a total force on it. For this next one, I want you to draw a free body diagram of this coffee cup. The coffee cup is just sitting on a table, but we're drawing the diagram for the coffee cup. So take a look. Think what forces are acting on the coffee cup. My cat really wants you to draw a free body diagram, apparently. So if you want, you can draw a free body diagram of my cat, and it will look the same as the free body diagram for the coffee cup. Again, I'm going to draw it as a box to represent my coffee cup, or drawing the cup free of everything else. You don't draw it sitting on a table. Our free body diagram is just the coffee cup. So if the coffee cup's on Earth, we know that gravity is acting on it. So we've got the force of gravity pulling the coffee cup down, but the coffee cup isn't falling down. So there's got to be another force keeping it from falling down, and that's the force of the table. The coffee cup is sitting on the table, and the table pushes up on the coffee cup to keep it from falling. And if you remember, we call that force of the table the normal force. So the normal force points upwards. So remember, the tail of my arrow has to touch the object, and I have to give this force a name tag. We said this is the normal force. So I'm going to label it F sub n. The F means force, and the N as a subscript is a name tag telling us it's the normal force. So the coffee cup is not accelerating up or down. What that means is that the total vertical force, the net vertical force, is equal to 0. So that means that the downward force should cancel with the upward force. So the length of my force of gravity arrow should equal the length of my normal force arrow. They cancel out, and that is why the coffee cup does not accelerate in the vertical direction. In this case, the normal force and the force of gravity have the same strength, the same magnitude, but they point in opposite directions. I want you to draw a free body diagram of the coffee cup again. So we're talking about the coffee cup. So in your diagram, the object that you're drawing a free body diagram for is the coffee cup. So yes, we have another object. Yeah, we have a deck of cards, but we're not drawing the free body diagram for the deck of cards. Our free body diagram is of this cup. So we only care about the forces acting on this cup, and the free body diagram should be free of all other objects. So the cup is still on Earth, so we've got gravity pulling it down. What other forces do we have? Well, that deck of cards is pushing down on the cup. So the cup also feels a force downwards from the cards, and I'm going to call it F cards. So force of the cards. Now, we know the cup is not accelerating up or down, right? It's standing still. So that means that the total vertical force, the net force, has to be equal to 0. And so you're like, duh, the table, the normal force is pushing up. Yes, but the key is the length of my normal force arrow. The upward force should cancel out with my downward force. In the previous example, the length of our normal force arrow was equal to the length of the force of gravity arrow. In this case, we've got two downwards forces. We have gravity and the force of the cards. So the table has to push up even harder to cancel out both of those downwards forces. So the length of my normal force is going to be the length of both of these downwards arrows added together. So my normal force is going to be longer than the force of gravity. So because the upwards force has to cancel out all of the downwards force. And now our downwards force is both gravity and the cards. So the table has to work harder, push harder to keep the cup from falling through the table. If you drew the normal force arrow the same length as your force of gravity arrow, that would be wrong, because then you would have a net downwards force. So the upwards normal force has to cancel out all of the downward force, so the length of the upwards force has to be equal to the length of the two downwards arrows combined. Now, same situation, but now I want you to draw the free body diagram for the deck of cards. And so you're like, okay, the cards are on Earth, so we know gravity's acting on them. What else is acting on the cards? Well, the cards aren't falling down, right? Gravity's pulling them down, but they're not falling, so there's got to be something pushing them up. Well, I think it's the coffee cup pushing it up, but what about the table? Isn't the table also like keeping it from falling? Well, before I answer that, I have a question. Can I apply a force on something without touching it? I'm gonna try to apply a force on the deck of cards. I'm gonna try to push it off without touching it. It's not working too well. All right, I'm trying to push it, but I'm not touching it. Oh, but if I touch the cards, then I can apply a force. Okay, so I can only apply a force if I'm touching the object. The only exception to that is the force of gravity for now. The force of gravity is a field force. So the Earth causes the force of gravity. You don't have to be touching the Earth to feel gravity, right? Like you could be a bird flying through the air and that bird still feels the force of gravity even though it's not touching the Earth. So gravity acts at a distance. But besides gravity, in order to apply a force to an object, you have to be touching the object. We call those contact forces, because in order for the object to feel a contact force, it must be in contact. Back to my deck of cards. My deck of cards are touching the coffee cup. Deck of cards is not touching the table. So the only thing that could apply a force upwards on the deck of cards is the coffee cup, because the cards are touching the coffee cup. And that is a surface, so you could call it the normal force. The table cannot apply a force on the cards because the table is not touching the cards. The table can apply a force on the coffee cup because they're touching, but the table can't apply a force on the cards, they're not touching. Okay, now I've got the yellow coffee cup with a frisbee on top of it and then a solar yard light on top of the frisbee. I want you to draw a free body diagram of the coffee cup. Okay, so you should be pretty cool with this. This one's not very different. So I've got the coffee cup. It's on Earth, so we've got the force of gravity down. What other forces are on it? Well, there's a frisbee on top of it, and there's also a solar yard light on top of the frisbee. But the solar yard light is not touching the coffee cup, so there is no forced solar yard light. The only thing applying a downwards force on the coffee cup is the frisbee because it's touching it. I'm going to draw a downwards arrow, call it force frisbee. And to cancel out those two downwards arrows, I have the table pushing up with a normal force, Fn, and that arrow should be the length of both of the two downwards arrows combined because there is a zero net force in the vertical direction. Now I'm going to add a deck of cards to the top of the frisbee. So now on top of the frisbee, I've got the solar yard light and the deck of cards. I want you to draw the free body diagram for the yellow coffee cup. So this one's not too different from the last one, but there is a small difference. Alright, so you've got the force of gravity, and it's the same length as the previous free body diagram because we're talking about the same cup. Then the only two things touching it are the table and the frisbee. So those are the only things that can apply forces. The force of the frisbee, let's talk about that first. Well, now on top of the frisbee, there is an extra deck of cards. So the frisbee is actually going to be pushing down more on the coffee cup than it was in the previous problem, because now there's more on top of the frisbee, And so now the frisbee is going to be pushing down harder on the coffee cup. So there's going to be a longer downwards arrow. Remember, the length of the arrow tells us the strength of the force. Stronger force, longer arrow. I've got 2 arrows pointing downwards. So I've got the table pushing upwards with a normal force, and that upwards normal force has to be equal to both of the downwards arrows combined together, so that there is 0 net force in the vertical direction. So because I've got more pushing down on the coffee cup, the table's going to have to push even harder upwards to keep the coffee cup from falling through the table. What if we have something moving? Okay, so I've got this teapot here, and I've got a string attached to the teapot. After this video, you can go spill all the tea to your friends about how to draw a free body diagram. That'll be quite the gossip topic, won't it? Notice that I have the string completely horizontal parallel to the table. So I want you to draw a free body diagram of this teapot that is moving at a constant speed across the table. Okay, so my object is now the teapot, and I can still draw it as a box. Okay, so what forces are acting on the teapot? So let's talk about the vertical forces first. So we're on Earth, we've got the force of gravity pointing down. The teapot is on the table, and that is the only other vertical force, so it must cancel with the force of gravity because the teapot is not accelerating up or down vertically. So the normal force has the same strength as the force of gravity, the same magnitude, same length. Now, what about my left and right forces? Well, I've got a string, and I'm pulling the teapot at a constant speed to the left. So I've got a leftwards force from the string. And if you remember what we call a force through a string, we call it tension. So I'm going to write it as F sub T for force of tension. The T is my name tag telling me that this is the tension force. On the AP test, sometimes they write tension as just the big capital T. Like instead of F sub T, they might just write T for tension, which is fine too. I prefer this method, but you can also use just the letter T. Now, is that it? Are those all my forces? Well, no. The teapot's moving at a constant speed, which means it's not accelerating in any direction. So my net force should actually be 0. All my forces should cancel out. So my up and down net force is 0. That's cool. But I've got this tension force to the left, so there's got to be something pointing to the right to cancel out that tension so that this thing goes at a constant speed. And you're like, frick, I don't know what that is. But you do. This one's a bit rough, but it's actually the force of friction that points to the right. And specifically, this is kinetic friction. So force of KF, as I'll call it, the force of kinetic friction pointing to the right. So the length of the tension arrow should be equal to the length of the force of kinetic friction arrow, because this is moving at a constant speed and all the forces cancel out, meaning there is 0 net force. So the magnitude of my tension is equal to the magnitude of the friction force. They point in opposite directions, so they cancel out, and the teapot does not accelerate. Okay, this one's a challenge question for you to try. So I've got tension in the string, okay? I'm pulling on the teapot, but it's not moving. So try to draw a free body diagram. It's going to look very similar to the previous one. Think about what type of friction is acting. Is it static or kinetic? Notice that a free body diagram doesn't tell you if an object is stopped or moving at a constant speed, because all the forces cancel out in both cases. Okay, the last thing I want to talk about is a little bit more complicated, but it's an important concept, super, super important. So I have my string attached to my teapot. And what I'm going to do, I'm going to pull it across the table again at a constant speed, but instead of pulling horizontally, I'm going to pull at a diagonal on the teapot. So the teapot's going to move at a constant speed, but I'm pulling at a diagonal. So I've got this tension in the string, right? Tension is pointed at an angle, which means that the tension has a horizontal part and a vertical part to it, right? I'm partially pulling up and I'm partially pulling to the left. So the tension has an up part and a left part. So I've still got the force of gravity, that's the easy part, Fg. And I've got a tension force that's pointing up and to the left at an angle. So this is my force of tension. And before I draw my other forces, because the force of tension points at an angle, we can break it down into its vertical component and its horizontal component. So it's got an up part represented by the blue line, and it's got a left part represented by the green line. So this is the horizontal component of tension, the part that pulls horizontally, and this is the vertical component of tension, Fty, which is the part of tension pulling upwards. Now before, we had the normal force pointing upwards and it was canceling out the force of gravity. Gravity was down, the normal force was up. They were equal and opposite. The magnitudes of the normal force and gravity were the same. They pointed in opposite directions, canceled each other out, which is why the teapot wasn't moving up or down. Well, in this case, teapot is still not moving up or down. So we know that the net force in the vertical direction has to be equal to 0 because it's not accelerating up or down. So there's no total vertical force. But now we also have tension, and part of that tension is pointed upwards. Tension is pulling upwards, and we've also got the normal force pointing upwards. But gravity hasn't changed. And we know that all those forces have to cancel out. So if gravity, which acts downwards, hasn't changed, that means that the total upward force has to cancel out with the force of gravity, which acts downwards. You can think about it this way. When I have the teapot just by itself here, gravity pulls down, the normal force pushes up. If I just pull vertically upwards on the teapot, so I've got some tension in the rope here. So what I'm really doing is helping out the table. So I'm pulling upwards a little bit with the string, and so now I'm helping out the table, which means the table doesn't have to push as hard to hold up the teapot because the string is holding up part of the teapot. So if I've got tension pointing upwards, that means that the normal force is going to decrease because the tension is helping the table out, essentially. So there I was showing you with just a vertical tension upwards. But if my tension is pointed at a diagonal, well, we said that this tension is partially pulling upwards. So I do have some vertical tension here, pulling the teapot upwards, helping out the table, which means that the normal force is going to decrease. My normal force is going to be smaller than the force of gravity. Because we've got a vertical component of tension pulling upwards, the table doesn't have to push up as hard to keep the cup from falling through the table. The vertical component of tension plus the normal force are going to cancel out the force of gravity. So the length of the vertical component of tension plus the length of the normal force arrow together should equal the length of my force of gravity arrow, so that the upwards forces cancel with the downwards force of gravity. Now, there's actually one more force. Because this is moving at a constant speed, there's no acceleration, which means our net force is 0, which means all the forces need to cancel out. So we took care of our vertical forces, but we've got this horizontal component of tension pulling to the left. And if we left it like this, that would mean that this thing is accelerating to the left, getting faster and faster to the left. But that's not the case. It's moving at a constant speed. So there's got to be a force pointing to the right to cancel out the horizontal part of tension so that it goes at a constant speed. That force is the force of kinetic friction. And so how long should I draw my arrow? The force of friction should cancel out with the horizontal component of tension. The horizontal component of tension points to the left, and friction points to the right, and it has the same magnitude or the same length of arrow. This is the force of kinetic